Hello and welcome to lecture 48 of the course Computational Complexity. In the previous lecture, we saw promise problems and then we saw the unique set problem. Right? So unique set is just like set, but with the promise that the number of satisfying assignments for the given Boolean formula is either 1 or 0. And we have to determine which of this is the case. And then we stated the Valiant Vazirani Theorem, which said that if unique set has a polynomial time algorithm, then NP is equal to RP. Or in other words, since we believe NP is, or since we feel NP is unlikely to be equal to RP, it is unlikely that a unique set will have a polynomial time algorithm, right? So this is the Valiant Vazirani theorem. So now in this lecture, we will see the proof of this fact, right? Okay, so the bulk of the proof can be stated in this following technical statement. Maybe I'll just give it a different color. Right, so maybe I'll give it green color. Okay. There is a randomized polynomial time algorithm A that takes a Boolean formula and reduces it to a another Boolean formula, or construct another Boolean formula, such that it's a reduction from a satisfiability to unique satisfiability, right? So it's actually a reduction from sat to unique satisfiability. So what does it do? It takes phi, a Boolean formula, as input and produces a phi, right? If phi is satisfiable, then a phi will be in the yes instance of unique satisfiability. So this is u sat yes. And if phi is not satisfiable, then a phi will not be satisfiable. So when I say unique satisfiability yes instance, it means a phi will have exactly one satisfying assignment, right? And with some probabilities. So if phi is satisfiable, then the probability that the reduced, or the a phi, which is the output of the randomized algorithm, which is another Boolean formula, the probability that a phi will have a unique satisfying assignment is at least 1 divided by 8n. And if it is not satisfiable, then if phi is not satisfiable, then a phi is not satisfiable with probability 1. So this is, the second clause is definite, this is for sure. If it's a no instance, meaning you start with an unsatisfiable Boolean formula, then we will get an unsatisfiable Boolean formula. But if we start with a satisfiable Boolean formula, we want to get to a Boolean formula that has exactly one satisfying assignment, and that happens with some probability, right? So unsatisfiable remains unsatisfiable, whereas satisfiable we may or may not get into the unique sat yes instance. So this is like a one-sided reduction, and also this reduction is a probabilistic reduction. So it's a randomized reduction from satisfiability to u sat. So using that, so now you may see the proof of how this implies NP equal to RP. So if u sat has a polynomial time algorithm, we have already shown if theorem 1 is true, that implies a reduction from satisfiability to u sat. So if u sat has a polynomial time algorithm, this implies that any language in NP can be reduced to u sat in randomized polynomial time, and then we can use the polynomial time decider of u sat to decide the original NP language. So we have a polynomial time algorithm, a randomized polynomial time algorithm for any language in NP, which is what the statement says, NP equal to RP, right? So that's the statement, and this is the main theorem that we will spend most of the time on. Given a Boolean formula phi, we will show a randomized procedure, randomized algorithm, by which we will construct another formula a phi, such that if phi is satisfiable, a phi is likely to have a unique satisfying assignment, and if phi is not satisfiable, then a phi is not going to have a unique satisfying assignment. or it is not going to have a satisfying assignment at all, right? So it will remain unsatisfiable. And the idea is very simple. phi is simply phi and with some another formula psi. Simply phi and with another formula psi, and where psi is randomly chosen. Okay, so it is immediately clear that if phi is not satisfiable, then phi also will not be satisfiable, because it's not possible to satisfy phi itself. So how can you satisfy phi and something else, right? So the second part, the fact that phi is not in sat, implies this part that I am underlying. This part is now immediate because of the construction of the formula a phi. What remains to be shown, right, is that when phi is satisfiable, a phi has exactly one satisfying assignment with a good probability, and the good probability we will shoot for is 1 divided by 8n. Sorry, 1 divided by 8n. And because it's one-sided error, we could easily boost it by just repeating, and we don't even need things like Chernoff bound. Okay, so what is the idea here? I'll first tell you very high level idea, right? So suppose what we'll do is we will choose a phi. So think about satisfying assignment. There are 2 power n possible assignments, right? So let it have n variables. Okay, so n is, in fact, I missed to say this, where n is the number of variables. So this 1 by 8n has n, where n is the number of variables. So there are 2 power n assignments possible, satisfying, non-unsatisfying, whatever, right? And we will choose the randomly chosen psi in such a way that psi will kind of cut many assignments. Psi will make many of the assignments as not satisfying. So if there were 100 assignments, psi will cut it by enough number so that what is likely to remain is exactly one satisfying assignment, right? So it is basically, you can think of psi as cutting every time you can, let's say you chop the space into half. So now whatever number of, let's say phi had 10 satisfying assignments, you can think of psi being cutting the space of satisfiable or all assignments many times, 2-3 times, so that 10 becomes 5, 5 becomes 2, and so on, and until it becomes, there is a good chance of getting a unique satisfying assignment. So basically psi just eliminates a portion of the assignments, making them unsatisfiable, and because it's randomly chosen, we expect it to also eliminate a portion of the satisfying assignments. So all that will remain is one small fraction of satisfying assignments, which we hope will be very close to 1. This is a very high level idea, right? So maybe just to draw a pictorial representation, of course I am drawing it in 2D, but thing happens in n dimension. So maybe psi is like a series of cuts of the half of the plane. So let's say first the bottom part is eliminated, this yellow part is eliminated, and with the second cut this part is eliminated, and with the third cut, let's say this top part is eliminated and leaving just one. So psi will be a series, you can think of it as a series of cuts. Okay, and what remains is every time, let's say the space becomes half, and what remains is very likely to be one satisfying assignment. Okay, so now we will see, so this is just a high level intuition. Now we will see the more formal parts of the proof. So what we will set psi to be, we want it to be a random function. So a randomly chosen Boolean formula, which we will derive from a random function. Okay, so psi will be derived from a random function h. So think of h as a Boolean function that goes from 0,1 power n to 0,1 power m. Okay, so n to m. And so we'll say what is m later, and psi is the formula that corresponds to if h of x is equal all zeros, right? So it's a random function. So roughly, so you will expect h of x will distribute, right, So it's like this. So this is it's a function from 0 1 power n to 0 1 power m. Right? So you expect h to kind of, it's a random function. So h will distribute all the inputs to a random output in the right hand side. So how many inputs do you expect to go to the all 0 output? You expect roughly equal number to go to each output. So you expect 1 divided by 2 power m of the inputs to go to the random, to the all 0 output, right? So you expect 1 divided by 2 power m of the inputs to go to be mapped to the all 0 output. So we choose h in such a way that or h will be chosen in such a way that the number of satisfying assignment will be roughly of the order of 2 power m, so that 1 by 2 power m of the inputs means it will be roughly of the order of 1, right? So again, what I said earlier, just written down, if phi had s number of satisfying assignments, right? If phi had s number of satisfying assignments, then a phi, which is just phi and psi, so it's just a fraction of the satisfying assignment that go to all zeros. And we have already said that the fraction is likely to be 1 divided by 2 power m. So it is likely to have s divided by 2 power m many satisfying assignments, right? So now all that we need to do is, what should be m? So for that we look at what is s, where s is the number of satisfying assignments. One may wonder, how do you choose s? But we'll explain that as we go along, because given a Boolean formula, we don't know if it is satisfiable or not satisfiable. Forget how many satisfying assignments it has, right? We don't know, we don't even know that. But our process will be such that even without knowing s, we will do something that gives us a good probability. So let's assume that the number of satisfying assignments is between 2 power m minus 2 and 2 power m minus 1 for some m. Okay. So we know that the number of satisfying assignments, it could be as much as all the assignments, which is 2 power n, or it could be as low as 0, right? So it could be anything between 0 and 2 power n, right? So, but let's assume that it is in the range 2 power m minus 2 up to 2 power m minus 1. Now, what is the probability that a phi has a unique satisfying assignment? And this is the most complex calculation that we will do in this lecture. When I say most complex, I mean in this lecture, but it's not very difficult. It's just very basic probability and conditional probability. So now what is the probability that a phi has a unique satisfying assignment? This is the probability that we are going to calculate. So in other words, the probability is taken over h. The number of satisfying assignments of phi being such that a phi has a unique satisfying assignment. What is the probability that this is incomplete, this is equal to 1. So a phi is nothing but phi and psi, where psi corresponds to h of x is equal to all zeros. So h of x is equal to 0 power n, right? So in other words, we can say one thing that we can do is we can consider this to be a summation over each x, and where x is each x, where x is from 0 1, where x is a satisfying assignment. Okay, where x is a satisfying assignment of phi. So what is the probability that this is likely to be the unique satisfying assignment for psi, or for a phi, right? Because if it is not a satisfying assignment for phi, it cannot be a satisfying assignment for a phi, right? So for each satisfying assignment of phi, we are seeing the probability that it can be unique satisfying assignment for a phi, right? And these are all mutually exclusive events, so you could just take the sum. There is nothing lost here. It's still equality. So what is in other words, what do we want? So we are only saying that if you look at all the satisfying assignment, let's say this is a set of all satisfying assignment. Right? We want this x to be alone mapping to all zeros, right? H should map this to all zeros. Everything else should not map to all zeros. All the remaining things should not map to all zeros, which is what I have written here. For all the y that is not in x, if it is satisfying phi, then h of y should not be all zeros. So I can further split it in the following way. Sorry. I'm sorry, I'm just a bit of technical trouble. I can split it like this. I can take the probability that h of x is all zeros, right, which is the first part, and this and can be split like, given h of x is all zeros, what is the probability that all the remaining y are not all, do not get mapped to all zeros. So there is a small typo here, do not get mapped to all zeros, right? For all the remaining y that are not equal to x, they do not get mapped to all zeros. So I will say it again. We want for each x that is outside summation, we want h of x to be mapped to 0, and for all the remaining solutions of phi, satisfying assignments of phi, let's say we call them y, that are not equal to x, we want h of y to be not equal to 0, h of y to be not equal to 0. And because we are multiplying these things, we need to make this a conditional probability. So this probability of a intersection b is simply probability of a into probability of b given a, right, which is what we have used here. Maybe I'll just write that. What we are using is probability of a intersection b is probability of a multiplied by probability of b given a. So a being probability of that hx, a being the event that hx is all zeros, and b being the event that for all y that is not equal to x, hy is not zeros, right? So what is probability that hx is equal to 0? So as I said before, hx is a random function. What is the probability that it maps an x into all zeros? It's just simply 1 by 2 power m, because there are 2 power m possible outputs, so this is simply 1 by 2 power m. Now we will focus the rest, we will just focus on the black part, which is the part that is written over here, probability that for all the remaining y's that are not x, hy is not all zeros. What we can do is to consider the complement event, right? 1 minus the probability that there is a y for which the h of y maps to all zeros. Sorry. So instead of saying for all the y's h of y should map to non-zero, we can say 1 minus the complement event being there is a y for which h of y maps to all zeros, right? Again the condition remains, the condition being h of x is all zeros. So we use complement event in the condition setting, okay, and the probability is taken over all the h. Now we have the second term, 1 minus probability of h. This probability term, now we can take each and every satisfying assignment of phi and check the probability that it is the h of y is 0. Okay, so instead of saying there exists a y for which the h of y is 0, we can just add up the probabilities of for each y h of y is 0, because all we are doing is we are taking the union bound of all these events, the probability that h of y is 0. So when we take the union bound, it is an upper bound, but we have a negative sign over here, so it gives a lower bound. So we have a union bound which is an upper bound, but we have taken the negative sign, so it's a lower bound. So what we are doing is we are replacing this probability with the summation over all the y's, such that y is a satisfying assignment of phi and y is not equal to x. Okay, what is the probability that h of y is 0 given h of x is 0? It boils down to that. What is the probability? So h of x being whatever it is, h is a random function. So what is x mapped to has no bearing on what is y mapped to. So this is simply the probability that h of y is all 0 is mapped to all zeros, or h of y is all zeros. Okay. So the probability is 1 divided by 2 power m. And how many y's are there? By assumption, we said that, let me turn up the light because it's getting dark. By assumption, we said that there are s satisfying assignment for phi. So there are s minus 1. So once we keep x aside, we have s minus 1 satisfying assignments y that are not equal to x. Okay. So this is simply s1 minus s minus 1 into 2 power n into 1 by 2 power n. So the red part was simply 1 divided by 2 power m, and the black part is 1 minus s minus 1 into 2 power m into 1 by 2 power n. So now fitting this back into this big the green square brackets, what we have is, so the outside summation still remains x being, so we are just moving back over from here, right? So this red part is 1 by 2 power m and the black part is what we calculated. So we just substitute it back 1 by 2 power m into this, and this summation. So now the inside part is independent of phi or anything, right? So now there are, how many terms are there? How many x's are there? The number of x's is simply s. So I can just replace the summation by just the quantity s. And if you just see what happens here, you have 1 by 2 power m in the square bracket minus s minus 1 divided by 2 power 2m, because this 2 power m outside and the 2 power m inside gives rise to 2 power 2m. Sorry. And now we want to lower bound this again. So we earlier said that s lies between 2 power m minus 2 and 2 power m minus 1. So the lower bound of s is 2 power m minus 2, right? And let me use a different color, red maybe. And the upper bound of and this s minus 1 needs to be upper bounded because it's negative sign. So that is, we take the upper bound because of the sign, and we can take this 2 power m outside. So this 2 power m comes outside, and what we get is 1 by this reduces to 1 by 4, and this becomes 1 by 2. So 1 by 4 multiplied by 1 minus 1 by 2, which is 1 by 2 again. So this probability turns out to be 1 by 8. So all we did is a simple calculation of a random function. What is the probability that this random function maps a certain value to all zeros, right? This is what we are doing here. So the probability that it maps x to all zeros is 1 by 2 power m, and the rest was just a standard separation of probabilities into different cases and adding them up, adding or subtracting them up. So we get that so what we get at the end is, what is the probability that ax or a phi has a unique satisfying assignment, that is 1 by 8, provided phi has a satisfying assignment in this range. in the range 2 power m minus 1 and 2 power m minus 2, right. If it has in this range, the probability that a phi has a unique satisfying assignment is 1 by 8, right. But you may notice that we choose m, the number of bits m, in such a way that there are roughly 1 by 2 power m probability. There is roughly 1 by 2 power m probability of hitting the a satisfying assignment being selected. So if there were more satisfying assignments, our m would have been bigger. If there are less satisfying assignments, our m would have been smaller, right. So this is what I meant by cutting it to the correct, into the correct size, to whatever is the required size. But how do we choose the m itself, right? How do we choose the m? Because we don't know, forget the number, we don't even know if the given formula is satisfiable. Again, what we do is we again go back to randomness and we choose the probability of, we choose m randomly, right. So we know that the number of satisfying assignment could be as high as 2 power n and as low as 1, right, assuming it is satisfiable. The unsatisfiable case we don't care at all, because we are just taking the AND with another formula. So the unsatisfiable formula remain unsatisfiables, right. So m could be as big as, so this 2 power m minus 2 or 2 power m minus 1 could be as big as n. So m should be chosen, could be as big as n plus 1 and could be as small as, the lower bound could be as small as 1. So m could be as small as 2, right? Because 2 power m minus 2 has to be equal to 1, right. So we choose m from this range 2 to 3, 4, 5 up to n plus 1 uniformly at random. And out of these choices, so any of these choices, there are n such values, 2 to 3 up to n plus 1, and any of these possibilities occur with probability 1 by n, okay. And with probability 1 by n, you are in the correct window where the above probability calculation applies, right. So if the formula is satisfiable, the probability of choosing the correct m is 1 by n, multiplied by, given that we chose the correct n, what is the probability that the resulting a phi has a unique solution? It is 1 by 8. So we get it is 1 divided by 8n, which is what we said we will do. So the probability of, so we don't need to know what s is, right. That is the nice thing about this. We don't even need to know what s is. If there is a unique if it has some satisfying assignment, there is some m for which that s falls in the correct window, and that happens with probability at least 1 by n. And once we choose that correct m, the probability of a phi having a unique satisfying assignment is 1 by 8. So it's 1 by n multiplied by 1 by 8, at least this, right. So it is 1 by 8n. So we have shown that by a random process we could convert phi to a phi in such a way that if phi is satisfiable, a phi is satisfiable, a phi has a unique satisfying assignment with probability at least 1 by 8, and if phi is unsatisfiable, then a phi is also unsatisfiable. So SAT gets reduced to unique SAT with probability at least 1 by 8. Okay. So now let us it seems like we are done. We are not done. We'll see why. We said that we need to choose a random function from 0 1 power n to 0 1 power m. How many such functions are there? So given each input, the input is an n bit vector, there are 2 power m possible values to assign, right. So 2 power m possible h could be any of the 2 power m possible values. So there are 2 power m whole power 2 power n such functions. So what I mean is 2 power m whole power 2 power n such functions. This is simply nothing but, in other words, this is nothing but, maybe I'll just write it outside. This is nothing but 2 power m multiplied by 2 power n, right. This is the quantity. And to specify a function that out of this many functions, we need to describe it with the log that many bits. So the number of bits required to describe this function is nothing but m times 2 power n random bits are necessary. So just to choose a function from all the functions require m multiplied by 2 power n random bits. So just in the time we take to generate these random bits, even if each random bit is generated per one time step, even this itself is more than polynomial, right? This is not polynomial, or this is not desirable because this is super polynomial size. Super polynomial means something that is bigger than polynomial, right? So the number of bits needed to describe this function is super polynomial. And recall, our goal was to do a reduction in randomized polynomial time. There is a randomized polynomial time is what I said at the beginning, right? Randomized polynomial time algorithm A such that which takes as input a formula phi and outputs a phi. So we cannot do that, right? This is not possible. So what else can we do? So what we notice here is, where did we use the loss of probability here? So we use the loss of probability at two places, I think, or we'll use the when I mean loss of probability, we use it throughout, but where did we use the function specific probability? One is over here. We said that the probability of a specific x going to 0 power m is 1 divided by 2 power m. This is one place where we use probability, right? And the second is this point. The probability that hy is equal to 0 power m given hx is 0 power m is 1 divided by 2 power m. So here it's like independence that we are saying, right? Regardless of what x, suppose we didn't know what x was, what is the probability that hy was 0 power m? It would be 1 divided by 2 power m, right? But now we are saying that even given hx is 0 power m, even then it remains the same. So it is like an independence. So these are the two places where we use, I will erase this here and here. These are the two places where we use the probabilities of the function. And these are the only two places where we use the probability of the function, right? And the rest was just arithmetic and calculation. So all we need is a random value should be mapped to all zeros with probability 1 by 2 power m. And even if x is mapped to 0 power m with 1 by 2 power m, y should be mapped independently. So what we really want is not, we need not want all the functions. We can do with a restricted class of functions as long as it has enough independence in it, right? So what we want is, I am summarizing what we want here in these two rules. One is that given any x in 0.1 power n and any r in 0.1 power m, what is the probability that hx is equal to r? This probability should be 1 divided by 2 power m. This is property 1. Sorry, this is property 1. And second is that given xy, where x is not equal to y, and given rs in 0.1 power m, r and s may or may not be same, it doesn't matter. What is the probability that hx maps to r and hy maps to s? This should be simply the product of the probabilities, 1 by 2 power m whole squared, or 1 by 2 power 2m. Right? So this is the independence part. If this is true, you automatically see that the bottom part also gets true, because what is the probability that hy is equal to s given hx is equal to r? So it is the probability that hy equal to s and hx equal to r divided by the probability that hx equal to r, which we have already calculated to be 1 by 2 power m. So this is 1 by 2 power m. So this is what we used actually. This is what we used. So we used 1 and then this what we infer from 2. But notice that even 1 can be derived from 2 independently without, we don't need 1 stated explicitly, because given 2, we could just take the summation over all the possible different y's, right, for all the possible all the possible values of s. We can take the summation over all the possible values of s, and if you take the summation, you will get 1 by 2 power 2m multiplied by 2 power m. So 2 power m will cancel, and what we will have is probability of h of x is equal to r is 1 by 2 power m. So what I am saying is that given this, given 2, probability of, so if you just summation over all s in 0 1 power m, probability that hx is equal to r and hy equal to s, this is equal to it is simply summation over all s times 1 by 2 power 2m, which will be 1 by 2 power m, but this quantity is actually nothing but probability that hx is equal to r, right, because we are allowing hy to be, we are just adding all the possibilities that hy can take, right. So it is simply probability that hx is equal to r. So which is what is, this is exactly 1. Okay, so what we are trying to show, or what we really want, the property that we want, h need not be a completely random function, and it can be using a restricted randomness, and a restricted randomness is sufficient for us. Okay. And this particular restricted randomness that we require is called pairwise independence. So basically, pairwise independence means h should be chosen in such a way that the images of two x and y, two different x and y, should be fairly independent, should be independent. It may not happen that 3 different x and y, x, y and z, the images are independent. It is enough that 2 are independent, and that is good enough for us. And what we will see is that so we saw that the number of random functions is 2 power m multiplied by 2 power n, but we will now see a much smaller class which has pairwise independence, and we will see that it is sufficient to work in this class. Right? It is enough to work in this class. So let me define what is pairwise independent hash family. So these hash functions, these are called hash functions. So a family script h is called a pairwise independent hash family. So where h is all the family is functions from 0 1 power n to 0 1 power m. If it's the property 2 that I have written here, x and y are not the same from 0 1 power n, r and s are from 0 1 power m. If you randomly choose a small h from the family, right, what is the probability that hx is r and hy is m? This probability should be 1 divided by 2 power 2m. Now all that it remains to show for our earlier proof is that we can specify the random h in using polynomially many bits. M multiplied by 2 power n was not so polynomially many bits. So we will see one example. Again, there are different ways of constructing pairwise independent hash functions. We will see one example which is fairly simple and which will convince you that we can do this, and that would be enough for us to see the proof. Okay. So given x and y, two different x and y, we want h of x to be mapped to r and h of y to be mapped to x. So what we do is we have a matrix A, okay, and a vector M or vector B, and so A is m rows and n columns, right, and B has, sorry, I think I'm writing it wrong. B should be like this. B has single column, it has m rows. It's like this. But x is 0 1 power n, right? So x is 0 1 power n. Okay, so it's like this. So this ax plus b is the function. So we choose A randomly, B randomly. A is a 0 1 matrix, m by n matrix. B is a 0 1 vector, m of a length m. So we are now, how many bits does it choose to specify h? Once we fix A and B, the function h is fixed, and we require only mn bits to specify A and m bits to specify B. So we need only mn plus m bits to specify h. Earlier the number was something like 2 power m multiplied by 2 power n or something like that, right? So this was very high. 2 power m multiplied by 2 power n, and now we are seeing that it can be much smaller. So all that remains to show is this, and everything happens modulo 2. Okay, x is a 0 1 vector, ax plus b will happen in modulo 2. So now all that remains to show is that this probability satisfies this this condition that I have circled over here. When x and y are randomly chosen, or x and y are chosen such that x is not equal to y, and r and s are chosen, then the probability is of this happening is 1 by 2 power 2n. So suppose we choose x and y and r and s in this manner. What is the probability that hx is equal to r and hy is equal to s? So h is simply ax plus b, and s is simply ay plus, h of y is simply ay plus b. So these two has to be satisfied. Now I can rearrange this. If these two are true, then I can get that a multiplied by x minus y is equal to r minus s, and if you take the difference, you will get that once you solve for a, then you can get b to be r minus ax or s minus ay, but those two are equivalent, like you can use any one of them. Now this is asking what is the probability that a multiplied by x minus y is equal to r minus s. Okay, so what is the probability that a multiplied by a certain vector is r minus s? Okay, so I'll just explain. So this is a, and multiplied by a certain vector. So let's say this vector is x minus y. This is equal to r minus s. What we know now is that x and y are not equal. So that means there is some entry here. Let's say this entry, let's say the kth entry, that is not 0. So that is 1. Okay, kth entry is 1. Now look at the kth column here. So look at the kth column here. Suppose everything outside the kth column was fixed. Okay, all the a's except the kth column was fixed, and you multiply x minus y with the rest of a, and now we are trying to, and we know that the kth entry in x minus y is 1, and we are trying to get it to sum to a specific r minus s. Now whatever be the remaining entry sum, we can take r, there is only one value for each of the entries in the kth column here. That will make it happen to be equal to r minus s. So each of these has to be fixed to some particular entry. Since there are m rows, there are m entries in the kth column, that has to happen, or that has to be chosen in a way that is desirable for us. So each of these m entries has to be 0 or 1 depending on how the others are chosen. And whatever the others may be, we can just, whatever it is, we can determine the probability that the kth column happens to be the way we want it, and that probability is 1 divided by 2 power m. So each of these m entries fall in the correct way. Okay, and now whatever a is, once a is fixed, r minus ax is just another vector, and b we want to be equal to r minus ax. So again, b is just a vector of m entries. What is the probability that b is equal to that vector? Again, b was randomly chosen, right? Capital A was randomly chosen, capital B was randomly chosen, and each entry of b is equal to r minus ax. Again, there are m entries. Each one of them should be chosen in a similar way, in the favorable manner. So it's 1 by 2 power m for that as well. So this is 1 by 2 power m. The choice of A, and the choice of B is also 1 by 2 power m. So yeah, again I've written here, if x minus the ith column, so here I have said ith column, maybe I'll just change it to kth column. Since x is not equal to y, we know that it is not equal to, there is some entry of x minus y that will not be 0. So both of these are 1 by 2 power m, and the choice of A is independent from the choice of B. So this probability is 1 divided by 2 power 2m, right? So it is just, right? This is just multiplication that you can see, which is what we were seeking as well, right? So we wanted the probability to be 1 by 2 power 2m, and we have shown that it is 1 by 2 power 2m. And as I said earlier, it requires this description of A and B, capital A and small b, requires mn plus m bits, and you contrast this with what we had earlier, which was 2 power m whole power of 2 power n, which was much more than that, right? Earlier we required m times 2 power n bits. Yeah. So which is a polynomial number? This is a polynomial number. This is polynomial. Right. So summarizing, again, just to summarize, so now we have shown the existence of these pairwise independent hash functions, and if we can just use these hash functions instead of the random h. This will be a much smaller class of functions, but if we choose these functions randomly from this family, this will have the properties that we need. This will not have all the independence, but we don't need all the independence. This is to the extent of independence that we need, right? So we choose, so given a formula phi, we first have to choose m uniformly at random from this range, from 2, 3 up to n plus 1. Once we choose m, we choose, now we know what is m. Now we choose a function h, small h, from the pairwise independent hash family of functions. So we will basically, that means we need to choose a, capital A and small b. So this requires mn plus m random bits, and then you output the formula phi, which is the same as what was input, and a Boolean formula that checks whether ax plus b is equal to 0. Right? So the Boolean formula will have the same n variables x1 to xn, and it will check whether ax plus b equal to 0. So we can write that in a Boolean formula, and this formula we know that if phi is unsatisfiable, this entire thing will be unsatisfiable, and if phi is satisfiable, we saw that the probability of this formula having a unique satisfying assignment is at least 1 by 8n, and which is what we claimed. This is the proof of theorem 1. So I'll just summarize the proof of theorem 1 again. So given a formula phi, randomly we construct a Boolean formula a phi such that if phi is satisfiable, a phi has a unique satisfying assignment with probability 1 by 8n, and if phi is unsatisfiable, then a phi is also unsatisfiable. A phi is just an AND of phi with another formula, which will make sure that if it is unsatisfiable, it remains unsatisfiable, and if it is satisfiable, we want to cut down on the solution space. So to cut down, we need to know, or we would like to know how many solutions it has to begin with, and then we cut down the space accordingly. So we don't need to know the exact number, we would like to know the order of the number of solutions. And we choose H in such a way that the likelihood of the solution space being cut to some number that is close to 1 is high. But we don't even know the number of solutions, so we randomly choose that number as well, right? And finally, we saw that the number of random functions, we cannot choose from the space of all the functions at random because the number of functions is high. Even to specify a function at random requires exponentially many bits. What we will do is that we will choose from a smaller family of functions which has all the required properties that we want. This family is called pairwise independent hash family, which has the property that we want, that is that for two values x and y where x is not equal to y, property that hx is equal to r and hy is equal to s is 1 divided by 2 power 2n. And we finally saw how to construct this family, and one example of one such construction using just simple matrices and mod 2 arithmetic, right? And this family requires only polynomially many bits, much smaller than the exponentially many bits for if we chose the entire function space, right? So just to summarize the Valiant Vazirani theorem, which said that if USAT is in promise P, right? If USAT has a polynomial time algorithm, then so maybe I'll just write promise P. Then the claim was that NP is equal to RP. So given any language L in NP, we can reduce it to SAT in polynomial time, right? That's because SAT is NP complete. Now we will show that SAT is in RP, right? Why? Because so given a Boolean formula, we want to solve SAT, satisfiability. We have already seen by theorem 1, we have seen how to construct a formula A phi such that it has a unique satisfying assignment with high probability if phi is satisfiable, otherwise it does not have any satisfying assignment. Basically, we reduce SAT in a randomized manner to USAT, and then this USAT instance, the assumption is that USAT is in promise P, so we can decide USAT in polynomial time, right? We can decide by assumption in polynomial time. So we started with the random arbitrary language L in NP, we reduce it to SAT, and then we reduce it to USAT using a randomized reduction, and so that reduces any language in NP to we can decide any language L in NP in randomized polynomial time, which is RP. So we get one-sided error, that's why it's RP. And to improve the probability of success, it's not very difficult because it's a one-sided error, so we can just repeat. If any of the ones output it is satisfiable, we just output that it is satisfiable, right? Because whenever it's unsatisfiable, it's for sure it will always output unsatisfiable. So we can also improve the probability of success. So again, improving the probability of success will only require polynomially many iterations. So that concludes the probability of proof of Valiant Vazirani theorem. So this is interesting that even when you have this promise that the given formula has either 0 or 1 satisfying assignments, even then it is we don't expect that it is it has a polynomial time algorithm, right? So yeah, so that is the main takeaway from this lecture. So I've already summarized the proofs, and with that I think I'll conclude. Thank you.